Dear distinguished professors, colleagues, and participants, I greet you all with respect. First of all, I would like to express that I'm delighted to have been invited by ICCSA 2026. And this occasion, I would like to extend my sincere thanks to Professor Osman Bigarvasi and committees for such a fruitful and successful organization ongoing for the last 26 years, since 2026, with dedicated and devoted efforts. I would like to thank everyone involved for their kind invitation, for their hospitality. I would also like to extend my sincere thanks and gratitude to the Braga Portugal for their kind hosting. And the chairs of our workshop today will be me, Yeliz Karaca from University of Massachusetts, and Professor Dumitru Baliano from Lebanese University. Minglei Jo is our technical assistant who will kindly be assisting us today. Thank you all. Welcome to our workshop at ICCSA. We are going to start our workshop with the presentation of paper entitled Garbage Image Classification Using Residual Attention, CNN, and Hybrid Optimization based on FIRE algorithm with co-author Ahmet Sadiq, Nadia Al-Sadi, Viner Samawi, and Yeliz Karaca. Over to you, please present your work. Good afternoon. Good afternoon. My name is Viner Samawi. I will present the paper entitled Garbage Image Classification Using Residual Attention, CNN, and Hybrid Optimization based on Ferrari algorithm. As well known, sustainability become very important these days. So one of the things that we should consider is how to manage waste sorting and try to serve the problem or try to attack or address the problem of recycling with minimum efforts and minimum cost. So the World Bank estimated that global waste will reach 2 billion and a half tons by 2030, 3 million and a half tons about in 2050. The need to automate waste sorting is crucial because most people are still unaware of how to sort the garbage in proper way. So furthermore, human work in waste sorting facilitate the hard, time-consuming work of sorting through waste. So to enhance recycling efficiency and accuracy, advanced automated recognition systems are essential to address the issue associated with manual sorting, which is dangerous and expensive. So the problem statement is that the current waste management system faces insufficient amount of recycling and disposal due to the limited accuracy of the sensor-based methods. So if we use only the sensor-based method, some sort of problems will occur during the sorting problem. For that, identifying these garbage through image classification will help the sensors recognize better the objects they are wasted or need to be recycled. So garbage images could help recognize based on object shape, purpose, or a brand, not only on its chemical or physical properties. So this research addresses that gap and utilize image analysis and classification algorithm to accurately identify the categories, different types of garbage, thereby optimizing the waste sorting process. Now, research on garbage classification employs various techniques including machine learning, deep learning, and especially the particularly CNN, as well as support vector machine. Recently, the deep learning is delivered excellent performance as it will recognize features easily and could handle problems, and especially if it is complex problems. By utilizing predetermined model, transfer learning or achievement, superior results even with limited data could be gathered. So, however, because convolution neural network rely on back propagation, we decided in this research try to solve the problems we face during using the back propagation algorithm. So these challenges are relevant to vulnerability and local minima, sensitive weight initialization. The main contribution is to introduce a new Chatak map controls, initiate randomness to prevent poor setup, accelerate convergence, and avoid local minima. Combines residual attention convolution neural network with an enhanced backpropagation framework to solve the stagnation issues of fixed learning rates that often lead to suboptimal convergence. Deploying a hard strategy using the Fairley algorithm and admin W to dynamically fine-tuning the learning rates, preventing both the local minima and the overall regularization updates. Okay. So the proposed approach relates of several intelligent techniques. First, the dataset acquisition, preparing the dataset, and then residual attention, RACNN, will be applied to extract feature. Then we will improve the backpropagation part of the RACNN so that the learning process will be better and avoiding the local minima. This will be done based on the Fairley algorithm with the admin W optimizer for tuning. The developed garbage collection classification is implemented in two phases. The training phase fed the garbage images into the training RACNN for feature selection. Then we will initialize the backpropagation algorithm weight using the Chatak sequence, which is one of the problems that we try to overcome using not random weight initialization, but initializing weight through Chatak sequence, optimizing the backpropagation neural network weight using Fairley algorithm to establish well optimized. Then we apply the AddW to fine tune the model and dynamically update the learning rate. This is the RACNN layers. The Chatak weights. Now the weight initialized function is based on Chatak map given in equation 1, this one, where x nu is equal to sigma sigma multiplied by xn1 minus epsilon minus sigma x square n plus gamma. Xn represents the initial weight, r is the 5.8, and sigma is 8.9, gamma 1.95. And this stage, there are several substages as follows: backpropagation optimization, where the weight is adapted using the given function. And y is the actual output, and y schwa is the expected output. The weight updates are computed using a gradient descent, where the new weight is the old weight minus the differentiation of EWT with n. The learning rate multiplied by the differential error with the weight. Fairley and admin W for fine tuning used to escape local minima. We are trying to avoid the stucking in local minima using the admin W fine tuning. So This will explore the research space effectively as fairly attractive and proportional to the brightness seen by the adjacent fulfare. The variation of attractiveness with beta is, instance, is beta equal beta 0 epsilon minus gamma r squared. More effective brightness for fairly is J is determined by the equation given, where this part is the attraction part and this part is the randomization. Randomized particular alpha vector of random number drawn from the Gaussian distribution at time t. To coverage, the properly randomness should be gradually reduced using alpha equation.
Because remember what shows the screen.
Okay.
Well, please wait.
The complexity of alpha 0 is O1. Okay. Now, we applied the developed algorithm and model on the used dataset, comprehensive image dataset for garbage classification and recycling, which contains about 19,762 clear images categorized into 10 classes: trash, shoes, plastic, paper, metal, glasses, and clothes, cardboards, biological, and battery. As it is seen, it's not fully balanced. But as we are using the deep learning, it will be balanced automatically. Now, this is the initial or the setting of the parameters needed to train algorithm. The experimental results, we used accuracy, precision, recall, and F1 score to measure the performance of the developed system. So for the validation accuracy, we started from the blue line until we are here. Then we start training process. The training process, it's seen that is almost, there is nothing, there is no jumping, there is nothing. It is almost stable. And this will ensure that our developed system is keeping stable without being fall in local minima or any other minimas. So the curve shows a steady and rapid increase in accuracy, followed by stable convergence indicating the effectiveness of learning. This trend confirmed that the hybrid optimization strategy enhances training, stability, and enables the RACNN to achieve higher classification performance without any problem. Then we have also the loss function part. It starts to drop until it is almost stable. So which also proves that the system is almost stable. Now, also we have the confusion matrix. It's clearly seen that the matrix, most of it is zeros. There are here and there are some misclassification, and the misclassification is done. High diagonal and low diagonal values confirm that the model accuracy is strong. The confusion matrix shows that most misclassification occurred with clothing, misdefined as trash or paper or plastic. So to solve this problem, actually we need to combine the suggested image recognition system with the sensor so that it could easily recognize the paper and the plastic from other materials. So the best performance, we compared our model with other models. it's clearly seen that our model is dominating, and it's comparable to the mobile DVET, sorry, but still it has the higher accuracy, precision, recall, and F1 score. In conclusion, the proposed architecture consists of the 4 key components. The RACNN handles the precise feature selection from West images. Chautauqua map generates high-quality balanced randomized weight initialization for fairly gradient algorithm, optimizes initial network performance to prevent local minima. Then ADAM-W provides stable, efficient fine-tuning for deep learning. The proposed model achieves about 96.5% accuracy on the testing dataset, outperforming conventional baseline from the literatures across multiple evaluations. Now, for future work, for real world, West object shows considerable variation in shape and size. Standard statistic dataset often do not reflect its environment diversity. Therefore, developing a robust data collection platform or enhancing dataset through adversarial learning is essential. This means that we need to prepare a dataset that should contain many objects with variations, so that and we will try to make it sort of balanced dataset so that this will improve the training system we are using for the deep learning and to improve the accuracy. Moreover, most garbage classification systems only recognize a single object. It's better now to get images, as we said, combined from more than one object in trashes, and to train the system on it so that we could compare or improve real-world accuracy. Thank you very much.
Thank you for your work in which you have addressed the issue of garbage image classification, which is important for having environmental protection and recycling and overcoming the problems of manual sorting. The work has included residual attention conventional neural networks with an improved back propagation neural networks developed blended approach, as we have listened to, is applied to the garbage dataset to test its classification ability. The achieved accuracy for classifying garbage objects is very high, at over 96%. Would any of participants like to forward question about this work, please? I would like to ask one question, Professor Venice. For what other applications other than garbage classification can your blended approach be used or employed?
It could be used for any sort of data, because actually what's going on is that we developed the model and we use the dataset for the garbage as a testing dataset to check if it is working properly or not. It is a pattern recognition full system, and therefore any sort of dataset that we could train the system on could improve its accuracy. Also, we choose to use datasets with unbalanced datasets so that it is the hardest part. For this reason, it could be used with any dataset, especially if it is a balanced dataset. If it is not balanced, also will be handled. Local minima is avoided, and the learning rate is adapted. Therefore, it will get more accurate results. But is it only for garbage images? No, it's and for any sort of images. And I can guarantee you, it's not only for images, it's for any pattern. It could be also used for voice, for data, for any.
What would be the most main strength and weakness of this design?
Most of the time, the deep learning utilize a lot of resources, needs a lot of time complexity is very high. So this is the challenging problem. You need a very high performance computing to, especially if the data is big data. It's not a big data. We are using normal data. We didn't test it on a big data to check if this complexity reaches I'll need more significant computer performance.
Do you have any question? Thank you very much for your presentation and for your answers. If there are no further questions, we can go ahead with our next work and presentation, please. The next presentation is on the work which has the title of Hybrid Transform CNN Architectures for Robust Low Light Image Enhancement, co-authored by Yinan Yao and Susan Obeis.
Yes, I'm here. Can you hear me? Hello.
Oh,
It's on the screen.
Yes.
Yeah.
Can you see my screen? Good afternoon, everyone.
Yeah, fine.
Nadia is on the screen.
Good afternoon, everyone. My name is Yao Yinan from University Malaya. It's my great pleasure to present our work in hybrid transformer CNN architectures for robust low-light image enhancement. Low-light image enhancement has become an important research topic because images captured under insufficient illumination often suffer from many problems. These problems greatly affected the performance of many computer vision applications. So today's presentation, I will introduce the motivation of the work and our models and the experimental results. First, let me briefly introduce the research background. Images captured in low-light environments usually suffer from several common problems, including insufficient brightness, low contrast, amplified noise, and blurred image details. This degradation usually reduce visual quality, but also significantly affect downstream computer vision tasks. For example, in autonomous driving, poor vision deliberately may reduce object detection accuracy. In surveillance systems, important targets may become difficult to recognize. Similarly, medical imaging and mobile photo also require high quality enhancements under challenging lighting conditions. Therefore, developing an effective low-light image enhancement method is both meaningful and practical important. Next is my problem statement. Although many low-light enhancement methods have been proposed, several challenges still remain. Traditional images enhancement methods usually improve brightness, but they often produce over-enhanced images, color distortion, or amplify noise. More recent deep learning approaches achieve much better performance. However, CNN-based methods mainly focus on local features and often forced to capture long-range distances. On the other hand, transformer-based methods are capable of modeling global contextual information, but they usually require high computation costs. Therefore, the main objective of this work is to achieve a better balance between global illumination and local detail preservation. I will briefly review my existing methods. Traditional approaches including histogram equalization and Retinex theory, Retinex member, and Retinex former usually faces some over-enhanced detail loss and many problems. Recently, deep learning methods have become the mainstream. For example, Zero DCE performs enhancement with references images, while Enlightened GAN removes the need for paired training data. More recent transformer-based methods, such as LL-former and the Retinex-former, significantly improve global feature modeling. However, these methods usually have high computation complexity and memory consumption. Therefore, this motivates us to investigate hybrid architectures that combine the advantages of CNN and transformers. Now I will reintroduce our proposed framework. Our first model is the contextual transformer-based network. The overall architecture combines CNN and transformer modules. Specifically, CNN layers are responsible for extracting shallow local features, while the contextual transformer block captures long-range dependencies and global contextual information. This hybrid design allows us the model to enhance global illumination consistency while preserving important local structures. Compared with using CNN or transformer alone, the hybrid architectures take advantage of both feature extraction strategies, leading to more balanced enhancement performance. And the secondary model, we also investigate it's called the local global dual branch network. This model adopts a U-shaped local branch to capture fine-grained textures. It's utilized stepwise convolutions together with 7x7 kernels and layer normalization. This improve feature extraction efficiency while reducing the number of parameters. Meanwhile, the global branch is responsible for modeling long-range contextual information. By combining both branches, the model effectively balance local detail preservation and local illumination enhancement. For experimental evaluation, we train the model using the LL dataset, L and LLV real, LLV2 static, and X-dark. Among these datasets, LLV1 and LLV2 provide paired references images, allowing quantitative evaluation. In contrast, EX-dark doesn't contain paired ground truth images, so it's mainly used for the quantitative visual comparison. For quantitative evaluation, we adopted two common used metrics. It's PSNR and SSIM. This slide presents the quantitative comparison. Shown in the table, the contextual transformer network achieves the highest PSNR and SSIM values across most benchmark datasets. The local global dual branch network also performs competitively. These results indicates that both proposed architectures effectively improve image quality. Overall, the experimental results demonstrate that our methods consistently achieve strong performance on different datasets. Next is the visual comparison on LLV1. On the LLV1 dataset, the contextual transformer network produces more uniform illumination across the entire image. The brightness distribution appears more natural and consistent. Meanwhile, the global local dual branch network preserves local textures more effectively, especially around edges and small objects. These observations are consistent with the quantitative evaluation presented previously. And the LLV2 datasets, it also produces similar visual behaviors as text samples, of which this example is meant to represent the typical enhancement behavior of the proposed models on this dataset. Finally, we evaluate our models on the EX-dark dataset. Unlike the previous dataset, EX-dark contains real-world low-light images without paired ground truth. Therefore, our evaluation mainly focus on visual quality. These proposed models effectively enhance image variable and avoid several artifacts and preserving natural appearance. These results indicated good generalization ability in practical applications. Now, I would like to summarize the main findings. First, both proposed model consistency achieved high PSNR and SSIM scores, indicating accuracy, brightness, reconstruction, and effective structural preservation. Second, the contextual transformer network performs slightly better in terms of global illumination because the transformer module captures long-range dependencies more effectively. On the other hand, the local global dual branch network excels at preserving local textures and edge information through CNN-based feature extraction. Furthermore, stable performance on unseen datasets demonstrates the robustness and generalization ability of the proposed architectures. Overall, these results confirm that combining global contextual model and local feature extraction is an effective strategy for low-light image enhancement. This is the role of global context modeling. It's very critical for illumination consistency, and the transformer can capture long-range dependencies. And the local feature modeling focus on texture and edge preservation. CNN-based structures are effective for fine-grained details. We also have some limitations in this work, such as extreme low light conditions and noise amplification, detail over smoothing, color inconsistency, and computational cost. So our future work is proposed to improve extreme low light enhancement, better noise suppression, and preserve more high frequency details, enhance color consistency and efficiency and the real-time deployment. The main references used in the work are listed on this slide. Thank you for your attention.
Thank you for your presentation of the paper which has dealt with low light image enhancement, which is important in computer vision research. The authors proposed a contextual transformer-based model for low light image enhancements, and additionally examine a local global dual branch enhancement model as a comparative design. Are there any questions you like to ask regarding this paper, please? Please.
Hi. I just noticed that you used the signal, the peak signal to noise ratio to check the accuracy of your system, right?
Yes.
Hi. You used PSNR for similarity check, for noise ratio check?
Yes, I use PSNR and SSIM.
Okay, so you used PSNR. Did you compare before enhancing the image and after enhancing the image if the noise is reduced or not?
I think our work only focused on the PSNR and SSIM metric. It's performed better, but maybe it's we will focus on the comparison in the future work.
Okay, because you said that the enhancement is to improve the image and reduce the noise. That's right. Right?
Yeah.
Okay. For that, the PSNR is good metric, but did you check it before and after? That's what I'm asking.
Could you repeat the question because the network is so good?
Now, PSNR is used to check the signal to noise ratio, right? Peak signal to noise ratio. This means when you enhance the image, you are trying to reduce the noise in the image and improve the image, so enhancing it, right?
Yes.
Are you okay? Good. PSNR, you just measure it after the enhancement or before and after the enhancement?
PSNR before?
Before the enhancement of the image, on the normal image, on the actual image, and after you did the enhancement? Or only after the enhancement?
I think maybe after.
Only after. I think you would better to choose before and after to check if the noise is really reduced.
Okay, thank you.
You're welcome.
Okay. I would like to ask one question. What are the most leading advantages of contextual transformer-based model over other models?
I think hybrid model contexture, the CNN can catch local texture and the transformer can catch the long-range dependencies. So combine them together can have a better enhancement. I think it's the advantages of the hybrid contexture.
Okay. Another question could be this: other than images enhancement, are there other significant applicability areas? If so, what are they?
I think maybe we should improve our transformer for more complex data set and more scenarios.
Okay, thank you very much. Are there any further questions about this study and presentation? If there are no questions, we can proceed, I suppose. Thank you very much, Yunanjo. Shortly, in our workshop, we are going to listen to the presentation for the paper co-authored by Nadia Asi, Nadia El Saidi, Sudan Obeis, and Ahmed Sadiq. The title of their paper is Lightweight Ratio Guided Weight Scale Control for Backpropagation Neural Networks in IoT intrusion detection with binary and multi-class evaluation. Yes, you may kindly proceed, please, if you are ready.
Mike?
Hello?
Mike, his mic is closed. You stop. But his mic is.
Hello? I can turn your mic.
The problem.
Above the mic. Even above the mic.
Okay.
Remove the mic phone. I can't hear you. Hello, Nadia. Do you hear? Are you here?
We have another. Sorry?
Which makes my problem.
Yeah, maybe children. Many. Do you know her number or who is he? Do you know? Not yet. Not yet. Not yet. I can't tell you. I decided. So I will call her. Not so hot, yes. Nadia, Nadia Sege, Nada Asya, Sudan Obayız, Ahmet Sadik. If they don't, yes, we will move another parts. Okay. هي شغلتها اللي هي سجلتها انجليزي بس خفيفة. اوكي يعني نروح على اللي بعدها ولا طبعا. يلا She said the mic is not working. Okay.
So when you check the next one?
Yes. Okay. We can now move on to our next and fourth presentation at our workshop. The title of the paper is Performance Enhancement in Clustering Cloud Workload, Trace Big Data for Cloud Data Center, with the co-author Suhat Yurti, Susan Nakhandi, Susan Obeys, Haydar Hadi Mala, and Nur Amalinia Jamalidis. If you are ready, you may please kindly start delivering your presentation. Suhat, I think. No.
Please show screen.
What is the problem?
Sure. Here. All meetings in that program.
What's the problem? Why they cannot start?
Hi, Hassan. Are you here?
Smart. I saw, yes.
Good afternoon.
Finally.
Yes, Ms. Nada, we can hear you.
Okay, I am sorry, there is a problem in my laptop.
If you are ready, you can start, please.
Okay, ready.
Thank you.
Good afternoon, everyone. My name is Nada Asam, University of Technology in Baghdad, Iraq. I will presenting our work titled Lightweight Ratio Guided Wide Scale Control for Backpropagation Neural Networks in IoT Intrusion Detection with Binary and Multi-Class Evaluation.
Hello?
Okay, are you hear me?
Okay.
Okay.
Yes, we can hear you. You can start your presentation.
Okay, here is a quick roadmap. I will start with the motivation and problem we are addressing, then introduce our contribution and methodology. After that, I will walk through the model we developed, the data sets and experimental setup, and then move into results, comparison, and statistical testing. I will close with our conclusions and directions for future work. The rapid growth of IoT devices has massively expanded the attack surface for cyber threats. We now have billions of connected devices, each a potential entry point. At the same time, traditional signature-based intrusion detection systems can't generalize to unseen attacks, and the classical backpropagation training is often slow and unstable, especially on the kind of imbalanced traffic data we see in IoT networks. So our goal in this work was to test whether the weight scaling term, which I will call WS, can stabilize backpropagation training for IoT intrusion detection without adding extra complexity. The related work, recent intrusion detection systems research has moved in a few clear directions. One major line of work focuses on deeper architectures, shown by Panama et al. And Zhang et al. to improve detection accuracy. Another direction is deployment-aware design, such as the two-layer fog cloud IDS proposed by Roy et al., which explicitly accounts for IoT resource constraints. A third major theme is handling class imbalance through techniques like focal loss, resampling, and equalization loss, as explored by Dina et al. And Deng et al. And a fourth direction focuses on interpretability and efficiency using explainable AI and attention-based few short learning, as in the work of Al-Abadi et al. And Ahmed et al. What's missing across all of these directions is attention to the classical backpropagation update rule itself. Almost no one asks whether a lightweight change at the optimization rule can improve learning behavior. That's exactly the gap of our work addressed. The problem statement, classical backpropagation converges slowly, oscillates during training, and is highly sensitive to the learning rate. These issues are not just theoretical, they are amplified on IoT intrusion data, which is class imbalanced, noisy, and has complex decision boundaries between normal and mashless traffic. Now, momentum-based and adaptive methods like ADAM or RMS prop do help with this, but they add hyperparameters and computational overhead. So our open question was, can a lightweight trajectory-aware correction stabilize backpropagation without that added complexity? Our first contribution is the weight scaling mechanism itself, a low-cost ratio added to standard backpropagation updates, unlike ADAM or RMS prop. Weight scaling rescale the weights themselves using the ratio between consecutive parameters states, so there are no extra moment estimate or hyperparameters to tune. Second, we performed a rigorous binary and multi-class comparison evaluating on two different benchmark datasets. We found clear evidence that the weight scaling effect is highly dataset and contents dependent, which turned out to be one of the most important findings of this study. Our methodology has 3 steps shown there. First, pre-processing. We remove non-informative attributes, encode categorical features using one-hot encoding or factorization, normalize everything to the 0 to 1 range with min-max scaling, and handle any missing or infinite values. Second, the network performs a standard forward pass through the hidden layer and output layer, and propagates the error using the gradient of the loss with respect to the weights. That's the classical part. Third, we compute the weights scale ratio between the current and previous weight states, clip to the range 0.9 to 1.1 for stability, and fold that into the weight updates alongside the standard gradient step. The developed model, the architecture itself is intentionally simple, a single hidden layer with 64 neurons using the sigmoid activation, and an output layer that uses sigmoid for the binary task or softmax for the multi-class task. We use weighted binary cross entropy or softmax cross entropy as the loss, depending on the task. We evaluate on 2 benchmark datasets. IoT ID20 is a binary intrusion detection datasets, and the TON IoT is a multi-class dataset. Both datasets go through the identical pre-processing pipeline I described earlier, and we use the same stratified 70/50/50 train validation and test split for both, so the comparison is as fair as possible. Here is our experimental configuration. We use a single hidden layer with 64 neurons and Xavier uniform initialization, a learning rate of 0.1, batch size of 512, and train up to 200 epochs with early stopping. Once the validation loss reaches 0.1, the the WS clipping bounds are fixed at 0.9 to 1.1, and everything was implemented in NumPy and standard CPU. For evaluation, we go beyond simple accuracy. We compute precision, recall, and F1 score from the confusion matrix: true positive, false positive, true negative, and false negatives. Also, training time and McNemar's statistical test. I will come back to shortly. This broad view turns out to be essential for interpreting our results correctly. Here is our handling results on IoT ID20 standard backpropagation reaches 95.78% accuracy and 85.81% F1 score compared to 90.53% and 74.81% for backpropagation with weight scaling. So plain backpropagation is clearly ahead here. On TON dataset, the picture is very different. Backpropagation gets 94.01% accuracy versus from 93.75% for backpropagation with weight scaling, essentially a tie with a similar clause for F1 score. And here is the results continuous as a graphical with figures. Figure 1 and 2 shows the validation loss and accuracy for backpropagation with a weight scale ratio to the IoT ID20 dataset, and figures 3 and 4 show the validation loss and accuracy for backpropagation with a weight scale ratio to the TON IoT dataset. Looking more closely at the confusion matrices for IoT ID20 under weight scaling, both error types increase. False positive roughly double from 4,750 to 11,063, and false negative also rise from 531 to 794. In an intrusion detection context, thus significant false positive create alert fatigue for security analysis, and false negatives means missed attacks. So this error trade-off can matter just as much as the raw accuracy number. And here is the comparison to check whether these differences are real or just noise. We run McNemar's test on IoT ID20. The 5.25 percentage point gap is statistically significant with p-value less than 0.001, and it's also practically significant. That's a meaningful difference in deployment. On TON IoT dataset, the 0.26 percentage point gap is also statistically significant, simply because the sample size is large, but it is not practically meaningful at all. And for conclusion, to conclude, our findings reinforce that accuracy alone is not sufficient. Multi-criteria evaluation, including F1 score, confusion matrices, and statistical testing is essential in cybersecurity applications. The weight scaling term is a low-cost drop in addition to classical backpropagation, but its effect is dependent. It doesn't help uniformly across tasks. On IoT ID20, plain backpropagation wins by a practically meaningful margin. So the bottom line is that the optimizer tweaks need multi-criteria, multi-dataset evaluation, not just accuracy on a single benchmark. And for future work, we would like to learn adaptive weight scaling clipping points instead of using the fixed 0.9 to 1.1 range. Combine weight scaling with momentum or Adam style optimizers and test on additional IoT and IDS datasets with deeper architectures such as CNNs or LSTMs. We are also interested in class imbalance-aware variants of weight scaling for rare attack types and in evaluating lightweight weight scaling backpropagation deployment directly on resource-constrained IoT edge devices. And thank you very much for your attention. I am happy
This study,
to take any questions.
Okay, this study gives us insight into tackling energy consumption, enhancement in cloud data centers, and experimental results obtained by the work show that strategic workload distribution over data center machines improve resource utilization and reduce power consumption, which are important benefits in the long term. Would anyone like to ask a question related to the paper, please? No? I would like to pose one question. You have referred to the use K-means algorithm to group the 50 million task record executed in SQL server. Why did you choose this specific method rather than the other grouping methods? What has been your motivation?
Sorry, can you repeat the question?
Okay. You have yes, you have preferred to use the K-means algorithm to group the 50 million tasks record executed in SQL server, right? Excuse me, can you close this presentation? Can you close this presentation? Maybe she cannot.
You can start using.
Okay. You have preferred, yes, you have preferred to the use the K-means algorithm to group the 50 million task record executed in SQL server.
Why did you choose this specific method rather than the other grouping methods?
Okay, we choose this method not to add for the algorithm more cost. We don't need give more cost for this algorithm. So we need to add a term of consecutive weights.
Okay. Okay. Are there any further questions about this study and presentation? Okay. Thank you for your responses and for the presentation. Dear participants, let us now listen to the last and fifth presentation for this session. The work is entitled A Novel Pan-Sharpening Framework Based on a Tangana-Bayano Fractal Fractional Derivative by Husam Yahya, Nadia Al-Said, Arkan Raskin, and Yediz Karaca. You may please start delivering your presentation.
Yes, thank you, Professor. Do you hear me?
Yes.
A moment, please.
Everything's good.
You can see your screen. Choose the wrong presentation.
Okay. You can. Yes. Okay.
Can you see the screen?
Yes.
Okay. One moment. Hello, everyone. I'm Hussam Yahya from the Ministry of Higher Education and Scientific Research in Iraq. I'm presenting now my paper title, A Novel Presentation Framework Based on the Atagana-Biliano Fractal Fractional Derivative. Here are the core problems. Wait a minute, please. Here we deal with satellite images that have the same scene at different resolutions. And we need a single sharp color faithful product. The pan-sharpening does exactly that. It merges one high resolution panchromatic band with several lower resolution multispectral bands. So we have a satellite image that have multiple bands. The fundamental tension is that it's pushed for a spatial sharpness, and you distort the color, the product, the color, and you blur the structure. So we need a balanced way to pan sharp or fuse the images. For sensor like World View 3, where the resolution gap is 4:1, so we lose a lot of resolution, the trade-off is especially hard. So our goal is sharpen detail while preserving spectral fidelity. The classical pan-sharpening methods only rely on integer order operators. Here, all of these methods use integer order that only look at pixels' immediate neighbors in the image, so that we cannot see the non-local scale invariant textures. Quickly through three families: component substitution, IHS, and PCA, our Gram-Schmidt, is sharp, but introduces systematic color distortion in these methods. The multi-resolution analysis in the AWLP or HPF preserve color, but rings fine texture is distorted. And modulation is a nice composite, but it's more than that. It's Gaussian that treat edges and flat regions identically. So we need a new method actually to perceive color, also the texture. Here we propose on fractional calculus. It's extension on the integer calculus actually. The fractional derivative integrates over an extended interval rather than a single point. So when we differentiate a function, we actually use the integer order, not the fractional order between 0 and 1 or 1 and 2 and so on. Actually and regularly we use integer orders. The fractional order, which gives every output pixel implicit access to a wider spatial context in the image. The genuine non-local memory that catch that classical fractional kernels like Riemann-Liouville and Caputo are singular. They blow up near sharp edges and reintroduce instability between pixels, of course. The Atagna-Biliano derivative fixes this by swapping the power law for Mittag-Lafleur kernel, which stay bounded everywhere, yet remains non-local. Actually, in here, we don't introduce a new image processing method, but rather that we introduce a new mathematical method or a mathematical tool to reintroduce the pan-sharpening operator. Our contribution is we derive an isotropic Mittag-Lafleur low-pass kernel mathematically with exact series coefficients, not asymptotic shortcuts, and drop it into SFIM in place of the Gaussian. So we replace the Gaussian with a new kernel. Secondly, we add a fractal dimension parameters, which we call tau, giving a two-parameter operator that capture both non-local in memory and self-similar terrain geometry. We know that, or any researcher can read, is that fractal geometry deal with textures. It's a non-integer number that describes the texture of the image, if we use it in image processing, of course, but it has a lot of applications. The third one, we optimize those two parameters per scene over a 15 by 15 grid. This is come by our data set, of course, with the neighboring fixed at optimal 7 by 7 for the neighbors. The fourth contribution on 20 word view 3 scene against 7 classical methods. We try this data set with 7 other methods, which is classical ones, based on Ergas, SAM, and SSIM simultaneously. A first for a classic method. Our fifth contribution is an abeliation study to see how removing one parameter can affect the whole study. The pipeline for our method is that a single idea on the left. We swap the SFM Gaussian for the Mittag-Lafleur kernel. The whole idea is using the Mittag-Lafleur kernel for smoothing the image on a two-scale detail injection and local mean correction. Turning the PAN and MS, these are the two hyperspectral for the same image. The two parameters alpha and tau. Alpha is for the fractional derivative. The tau is for the fractal dimension. We use them and deduce the best values that minimizes Ergas computation. In the mathematical backgrounds, the framework rests on 3 building blocks. We have fractional calculus and fractal geometry and the Atagna-Biliano operator that combines them. So we use the Atagna-Biliano and fractional and fractal operators. Intuitively, the alpha controls non-local memory, the reach of the kernel, and the balance between edge sharp and noise. So we have fractal dimension that measure noise and sharpness in the image, while the fractional, while tau, the fractal dimension sensitivity to self-similar. The fractal dimension is used to measure the self-similar sets, or in general, the complexity of any texture, but is perfect for self-similar sets. The key property is that because the Ataganabeliano derivative use Metagla-Flare kernel, it is non-singular at the origin. The alpha at 0 is 1, unlike the Caputo and Riemann-Liouville kernels, which are diverge, of course. That is what let us smooth gradual transition without ruining sharp edges. We began our method by combining a low-pass kernel. We choose an Ataganabeliano normalized Metagla-Flare kernel from the equation, this equation. And of course, the Ataganabeliano kernel is 1 minus alpha plus alpha over gamma on alpha. The top line is the AB normalized Metagla-Flare kernel. Below it, the middle line is how we evaluate it, an exact truncated series. Actually, we truncate the series of the Metagla-Flare with no asymptotic substitution, so that the kernel is computed precisely. The bottom line is the discrete weights at each pixel offsets. So UV is the new pixels, actually, normalized to sum to 1, so it acts as a proper low-pass filter. The theorem at the bottom, we deduce that it's about the weights. The weights are positive and strictly decrease with distance, if we take the distance between pixels, of course. Closer pixels always counts more, which is what you want from a smoother to do. So we take this operator and make it to smooth the image. In the pipeline of our methods, stage 1 and 2, stage 1 simply low pass the pan band of the image with our kernel to get it smooth, spectrally consistent components. Stage 2 forms the modulation of the pan over smooth pan, which isolates the spatial detail. So we have isolation and smoothing. In the parameter justification, clip bounds, its rule clips only genuine outliners. If we take the smoothing and the modulation ratio, of course, we will face genuine outliners. Band independence, so spectral ratios are untouched. In the honest point here, the appellation shows clamping is negligible and the dynamic range when delta is smaller than 0.005. Stage 3 and 4. Stage 3 inject two scale coarse detail, a luminance weighted additive term that preserve interband ratios, and the stage 4 is to emphasize a local mean correction. The two parameter optimization here is how we pick the parameters, the alpha and tau. The numbering is fixed at 7 by 7. We choose that for this specifically, actually. This for each scene, we choose an alpha and tau that minimize the air gas measure over a 15 by 15 grid. The bounds are non-arbitrary. They came straight from the operator. And because that's 225 evaluation are independent, the search is empirically parallel and adds a little overhead. The alpha, of course, is between 0 and 1. The tau, of course, is between 0 and 1. The decays by series convergence are the monodic decay of the theory. The grid is chosen to be 15 by 15, which actually equals to 225. Balance the resolution vs cost. Finally, we're piercing optimal cluster. These are the measures we use in our methods. Our 6 complementary metrics, it helps to group ergas, SAM, and SSIM are mostly about spectral shape and structure. The ergas is global spectral plus special error. So we have an error after the fusion. PSNR, SCC, and Q4 lean more on photometric accuracy and high frequency edges, all on 20 world view 3 scenes. We measure those 6 parameters over all the datasets on the reduced resolution protocol with full reference ground truth. This is our dataset. The data is band collection world view from a satellite's images as standards on the field. We choose a 20 test scenes, each with 8 multispectral bands and 265 and 256 on a co-registered pan at 4 times resolution, prepared with WARS protocol so that we have full reference ground truth. As the montage shows, the scenes span coastal, vegetated, urban, and mixed lands cover, a deliberately demanding diverse test set. In the experimental setup, we compare against 7 established methods, covering all 3 classical families: component substitution, multi-resolution analysis, and modulation transfer, so that the compression is fair across the whole landscape of the dataset, of course. The one to watch is AWLP, the strongest competitor on this big benchmark. The strong competitor is the AWLP. For our method, we run per scene grid search over alpha and tau with the neighboring 7 by 7. We remember that ergas and SAM is lower is better, and SSIM, PSNR, SCC, and Q4 is higher is better. This is our results with these data sets. We can see that the headline numbers averages all 20 scenes. Our method is the highlighted bottom row, takes the best ergas at 4.768. The best SAM is at 5.78 degrees, and the best SSIM is at 0.8761. The line to land is the bottom. No classical method on this benchmark has previously been best on these 3 at once. So this is our powerful method, actually. The power in our method is that. Note also that just replacing the Gaussian moves SIFM ergas from 5.168 down to hours. The kernel substitution alone is doing real work. In the experimental results here, the radar view summarize all 6 metrics. 2 things to take away. First, our SAM advantage is not an average artifact. We have the whole spectral angle on every single one of the 20 scenes, without exception. So our method worked for all of this. The second, the AWLP keeps on the lead on the PSNR, SCC, and Q4. Actually, this is the strongest competitor to our method, the AWLP, because it's multi-scale wavelet injection. The wavelet injection is a very hard to beat, actually, which recovers high-frequency edge energy that our single-scale method cannot reach. So we occupy the largest overall area. And the honest reading is that the 2 methods are complementary. You choose based on the weather, or you take care about spectral fidelity or edge sharpness for this data set. Here we do an ablation study the appellation tells us which component does what, and the separation is clear. The metaclophyr kernel substitution alone drives the air gas gain over SFIM, over 5.168 down to about 4.75. The spectral angle gain comes entirely from the local mean correction. If we remove it, and Sam jumps right back from 5.7 to 5.8 degrees, exactly the uncorrected value. This is our cleanest designed justification. We varied the kernel size, so vary the neighboring size of the image. And the relationship with air gas is non-monotone. An inverted U, we can see on the figure, of course, 3 by 3 is too small for the metaglyph decay to develop. It's non-local character. A 9 by 9 over smoothness and inflates air gas by 17.4%. So 7 by 7 is the unique optimum. Crucially, 7 by 7 win all 20 scenes without exception, which is exactly why we fix the neighboring rather than searching it as a third parameter. We don't search it, actually. We tried it. In here, the parameter sensitivity. This is the parameter sensitivity picture on scene 1, our harder scene, actually. The heat maps show the alpha is the controlling parameter. Alpha has more gain, actually, in here. The tau has a comparatively weak effects. For this heterogeneous coastal texture, the air gas keep dropping as alpha goes 0, a broad, maximally non-local kernel. Across the benchmark, the optima genuinely vary. Alpha from 0.05 to 0.75 tau, and the tau is from 20 to 0.8. No single pair is the best everywhere, actually. That variation is the empirical justification for optimizing per scene rather than calibrating one fixed pair. In here, in the visual compression, a qualitative look on the scene 16.
زين هو شنو عنده مايك لو شلون؟ هو حسام.
A dense urban area with the fine tree structure. At a full scene scale, the good method looks similar, actually. The differences show up in the zoomed crop. This is the zoomed crop. Our method keeps both the spectral character of the rooftop materials and the sharpness of the street boundaries. So we can see that the alpha is more useful on the vegetation areas, and the tau is more beneficial from the high texture images. In the conclusion, we replace the SIFM Gaussian with metaclophyr kernel. This is our whole method. The orthogonal fractal fractional derivative on a 20-word view scene against 7 methods. We also learned why the local mean correction is the sole driver on the spectral angle, and 7 by 7 is the unique neighborhood. The broader message is that these weights are derived from an operator with known mathematical properties, not tuned by trial. In the future work, we propose a multi-scale metaglyph kernel pyramid mirroring AWL to close the PSNR, extension to hyperspectral pan-sharpening, where non-locality and scale invariance may help more. The border message actually is embedding the kernel as a learnable convolution nail in a network, and the frequency selective mean correction to recover PSNR without sacrificing SAM. And thank you, and happy to take questions.
We thank our colleagues for their work, which is on pan sharpening, which is challenging because of being demanding in terms of improving spatial details, compromising spectral accuracy and preserving spectral fidelity. which blurs spatial structure. What is introduced in this work is ABRFFD as pan-sharpening framework that replaces the conventional Gaussian smoothing kernel with left-eye low-pass filter derived from the Atangana-Baliano fractal fractional derivative. Does anyone like to forward a question to our presenter?
I'm happy to take questions.
Can I ask a question, please?
Yes, of course. Please.
Okay. The proposed novel framework works on stellate images. Can you exemplify some other areas of applicability with regard to the approach you propose? Do you think it can be used for improving clinical medical images like MRI or CT scans in the future?
Yes, of course. It's not for this data set only. This data set is for testing, actually. I'm not using here any neural network or AI or machine learning. It's just steps. And look for the neighboring pixels. That's it. It's a very simple method, actually. And we can use it anywhere. I didn't test it on medical images, actually. I don't have the sufficient knowledge to be exact. But I'm sure it will be a good study, inshallah.
Are there any further questions about this study and presentation?
Online.
Online?
Yes, someone listening.
Sorry?
Yeah.
Yeah, you can ask, please.
Yeah. Good
Yes,
afternoon,
please.
everyone.
Good afternoon.
Sam, you said in the table that you previewed, you said that the most important results we have is the last row. It's your result, I think. But when we compare it with the previous row, we see the change is just 0.1 or maybe less. So this is effective, you think? You propose
the table, you mean, doctor?
The table, please, the table of your results.
Yes.
Compared with other results. If you see the last row before, if you see the row before the last one, we see the value is 4.7 something 9 or 8, and your result is 4. It's the same, just 0.0.
Just a few.
Yeah.
Yes.
0.1, not 1, not 0.1, 0.1 change. Do you think that this change is important to
yes, it's important so that
methodology or something like this? I don't know really. I just want to ask.
Yes, I hear you. Can you hear me, doctor?
Yes, of course.
This I find it significantly useful, actually. I can get a better ergas. Let me actually represent and show you.
Mm-hmm.
You mean that?
Yes, exactly.
I can make the ergas much better than this result, actually.
Yeah.
But I want it all better, not just one parameter.
Hey, but just see the enhancement is just, for example, 4.768, and the previous one is 4.77. So this change, or this small change, is effective, you think? I don't know. Maybe in your work, it's very effective.
In the multispectral images, yes, it is very effective.
Okay.
In the multispectral image, exactly.
Thank
in
you
these data sets, yes.
Thank you very much.
Thank you.
Okay. Are there any further questions? Okay, thank you for your presentation and for your responses. Dear participants and colleagues, this brings us to the end of this session.
Dr. Elise, I have a presentation at 5. but there is due to some electrical problem, I can't submit it in this session.
Okay, you can present. Go ahead, please, if you
Okay,
wish.
thank you very much. Thank you.
Thank you.
So
Second
I will
slide.
share. Yes, thank you very much. Share. And you see the PDF. Just 1 minute, please. I need to go to this room. Yeah. Just 1 minute. Yes. You see my presentation?
Yes, yes, please.
Thank you. So, good evening or good afternoon, everyone. Thank you for attending my presentations. Today, I will talk about very important subject is how we enhance the performance of cloud workload, especially for big data in the cloud data center. Okay, and this presentation is submitted by Suhad Yusuf and our college. The motivation for this work is what we have really. Just sorry, 1 minute. The cloud computing now it's a foundation of modern digital infrastructure. As you know, everything now, even in our iPhone or any other phone, we save all information of us in the cloud. So it's a foundation of modern digital infrastructure. However, massive data centers consume an incredible amount of electricity. You know, let the data center work, they consume a very incredible amount of electricity, leading to what? To operating cost and high carbon footprints. Okay, so the traditional virtual machine scheduling, we need to schedule the job that come to the cloud, okay, and data center, so you can run it. The traditional one use a lot of method or say traditional method like round robin or other method, okay? They don't care about how we can distribute this workload to reduce especially the power management. Why? If you reduce it, it will reduce the carbon, it will reduce the electricity and everything. So we here, the key contribution of our work, we introduce a new CPU management for jobs. It's called CPU-based allocation. Okay, that combine workload clustering with CPU-aware scheduling to improve the cloud resources allocation and reduce energy consumption. How we can think with this? What we need really in cloud computing, we need to improve the cloud performance, we need to decrease power consumption, and we need to reduce CO2 pollution, and we need to minimize the processing time. If we can achieve all these things or some of them, it will be perfect. Okay, so we propose a methodology that contains 3 stages. The first stage is data acquisition and preparation. And for this work, really, the data is 45 gigabytes. It's very big as a normal data for us, okay? So we have to use a lot of software to open this data. It's called a Google Cluster Trace for 29 days, okay? That all the machine in the data center work. So we need to get this data set, we need to change it in a format that we can, structured format because it's unstructured, okay? So we start steps for this data collection using tools, data cleaning, we remove everything that is noisy or outlier, and then data normalization, we change the data to be in a structured format, and then finally, we have a CPU rate extraction. We just use from this data 50 million records. Then the next step, we use a k-mean clustering. Why k-mean clustering? Because it's the simplest clustering method. The main idea is the clustering is the simplest clustering method, and we can get the centroid value for it. Okay, so we don't need density like dbScan or other type. So we use k-mean. We divided the cluster to 3. And we can divide it to 4 or 5 or 6, depend on our proposed methodology. Okay, so we have low CPU. It means the job that needs low CPU, and job that need medium CPU, and job that need high CPU. Okay, then after that, when the incoming jobs go to the cloud, they do a classification for it. They divide it. It's like something when we divide something, we can run it on this machine, run this on this machine. Why? To reduce the energy and make all the machines work at the same time. Okay? And then we have sorting and grouping to the jobs, and then VM allocation, virtual memory allocation. We allocate job to a specific server. Then we run this job, okay, and we see the performance evaluation or the results of this job. Okay, so this data that we talk about it, we release data, we record a period of data because 25 days, as I said, okay, in a single cluster, in a data center. And we have approximately 12,500 machines work in this data center. And the number of users with the resource usage is request like 925. Okay. So this is the tables found in this data set. Okay, so we choose one of these tables, which is the task resource usage, how we can make the usage of the resource that we have it. This is a statistical, I already talked about it. It's 400 trillion, the size of records, which was just 50 million, because the computer that we use is just capacity. And we now download this data by running some program until we get the data from the Google Trace. So we have an account in Google. We use a tool called GStootle. Then we write a code to extract the data from Google directly, and then we take this data. This data is not normalized. What I mean by this, it means I can't use this data in any type of algorithms that we can run it in a computer. So we normalized it in a structured format to deal with it and save it in a file for or an SQL server for later use. So the proposed methodology, CPU-based allocation steps, we need to request the data, we classify it, we sorting the data, combining it together into groups, and then run the job that we ask for it, and then we do the virtual machine placement, and then virtual machine allocation, and submission the results of this job. What I mean by results of job, for example, I asked from a cloud to give me a RAM of like 128 gigabyte. So this is the job that I asked it from cloud. Okay, so we classify this job. For example, we have a bulk of job. This job be here in this group, the other job in another group, and the other job in another group based on what? Based on the CPU. We say that we have low, medium, and high CPU rate. Okay? As I said, low, mid, and high CPU. Then we're sorting it from the lowest till the highest one. Why? So we can divide, for example, so they give the lowest one to machine that working, for example, with memory. They don't need a CPU. They just need a little of CPU and so on. So we divided them into a data center in a way that we can make all the computers or all the servers work in a way without energy consumption, a lot of energy consumption. Okay. This is submission that, as I said before, I discussed it. And this is the result of 3 clusters that we have it. We have 3 clusters, minimum CPU, medium, and high CPU. Okay. Then we make allocation. We know that we have a virtual machine allocation and physical machine allocation. The physical machine allocation is the real computers or server in the data center. Okay. So we send the job to this physical machines in data center. Really, we get a lot of results. The best important thing is result. In this result, we have reduced, and you see what it's related to the energy. We have reduced. The improvement in our method is like 17.5, reducing the electricity consumption, the energy consumption also, consumption, sorry, and the CO2 footprint. So, discussion for our work, why we did use CPU-based allocation outperform, why it's outperform the default scheduling, because the incoming task first, it will be classified according to the CPU demand before the allocation. Okay, it have a better virtual machine utilization, since tasks with similar CPU requirement grouped and mapped to appropriate virtual machine, and they reduce resource waste, fewer underutilized resources, reduce unnecessary processor activity, and they improve the energy efficiency, since the balanced workload distribution lowers the overall power consumption. And thank you very much for your listen. And just sorry for my breath, because I just come now from work. I am so tired, sorry. So thank you. And any question?
No worries. Thank you for your presentation about your work. Concerned with the challenges of growing IoT technologies. The authors of the work have proposed weight scaling mechanisms that enhances standard backpropagation by modulating the weight updates using information. Okay. Okay.
So if you have any questions.
Yes. Do you have any questions?
Hi, Suhad. How are you?
How are you?
Well, I miss you so much.
Hello, Doctor. How are you? Thank you very much. I miss you too.
Suhad, you were talking about the using virtual machines in cloud computing, right?
Yeah.
So you are using data set. How much is the size of the data set?
The real size is 45 gigabytes, but we use just 50 million records from the whole data set.
Why?
Because we used first, before starting with big data and the tools of big data, we start with the SQL server. So there is a limitation in SQL server. For this reason, we use just 50 million to show the idea, because it's not, it's this real data from Google. We need to have an account in Google, but we need just to trace it in something called the cloud sim, a simulation.
Okay.
So the size, it's not matter. 50 million is enough to check if we allocate them.
We choose them randomly?
Choose what?
The 50 million out of the 44 giga?
Yeah.
Choose them randomly.
Yeah, from one of the tables. We have more than one table. From one of the tables, we choose it randomly.
So it reduces the time or what?
Yeah, it reduces the power consumption.
Power consumption.
If you see, Doctora, the presentation, we see a lot of things that it's the watts. We check how host watts per second. So when we use the first method, we use it's round robin. It's the standard one in CloudSim, okay? And all of us, we know what do you mean by round robin. And the other one is the clustering. So we reduce the watts per second in clustering method. So based on this, we in this table, if you see it, the space, the shared allocation policy, round robin, and the using Kuba CPU.
So this means the K means outperforms the round robin?
Yeah.
Okay. Thank you very much.
Thank you very much, Doctor, and we miss you a lot. And we hope with you now, but
yes, I will.
Visa. Okay.
Okay.
Question, please.
Okay. If there are any questions, okay. Thank you very much, Suha. I wish next time we will meet again. Yes. Dear participants and colleagues, this brings us to the end of this session. I would like to thank each participant for their valuable contributions they have provided through their papers and presentations. Next section will start, 1 hour after. Yes. Thank you very much. See you, Suhat.
Thank you very much, Doctor. Thank you.
Excuse me, the session is supposed to start now, actually.
Okay. Okay.
Hi, I'm Giulio Biondi. I'm the technical assistant for the session 3H.
Okay, I see. Same session will continue, or I assume?
The session is scheduled to be at 4 p.m. Portugal time. So
yes, okay, we can. Yes, okay. Thank you very much. I think yes. Okay, I'm checking again. Do you need coffee or something? Yes. You are Jolie Biondi, right?
exactly.
Okay. Nice to meet you, Jolie.
Nice to meet you too.
Okay, we can continue. Dear professors, colleagues, and participants, I greet you all with respect. Welcome to the subsequent session of our workshop. The first presentation we are going to listen in the session is about the paper entitled An Efficient Polynomial Framework for Optimal Control Applications in Network Protection and Solar Energy Systems by Balsam, Fuad, Suha, Sihat, and Sabah Hahan. Over to you, please, if you are ready.
Yes, I am ready.
Yes, please.
Good afternoon, everyone. My name is Bassem Fuad. I'm master research mathematical from the University of Technology, Baghdad, Iraq. Today, I am going my present our research entitled An Efficient Polynomial Framework for Optimal Control Application in Network Protection and Solar Energy System. Now, let's begin with the motivation of the research. Optimal control problems are difficult to solve analytically. The proposed framework improve accuracy, reduce computational cost. Goal.
Your voice is too quiet. Sorry, I interrupt you.
What? You can't hear me?
Yes, but I can barely hear you.
I can hear you properly, actually.
Okay. Complete?
Okay, we can continue.
Yes. Goal, the aim is to construct the extent complete vetable polynomial framework for efficient solving optimal control problems. Now, let's move to the problem statement. Number one, continuous optimal control are often difficult to solve accurately. Number two, exist approximation technique have limitation. Number three, many numerical methods require higher computational cost. Number four, there is a need for a robust and efficient polynomial-based framework that provides accuracy solution without requiring clause from analytical solution. Now let's move to the extent complete vetable polynomials denote ECV PPS, a new family of basis function as introduction. There are used a constructor of operational differential matrix. The method transforms the optimal control problem into a system of algebraic equation. This relation or this equation is denoted as defined the recurrence relation of the proposed ECV-PPS. Each polynomial in general is generated from the previous two polynomials. Now let's move to the application. The application one talk about cellular power system and optimal control problem. The state variables x of t stored represent the stored energy in battery, and the control variables u of t represent the charging or discharging signal. Solar panels generated electronic energy from sunlight, our objective minimum cost function. The boundary condition and the state equation x dot of t equal u of t, the right of the charge or stored energy equal to the control input. Goal, find the optimal control u star of t, the minimum j, while satisfying the system dynamic and boundary condition. The proposed method determines the control strategy u of t to efficient manage energy storage, minimize cost, and ensure the system meets the required final level energy level. Now look at about the numerical result. The x of t represent with the different n 4, 5, and 6 represent increasing n led to the smaller error. That mean confirm the efficient and confirm the proposed method. And now the figure represent the absolute error of the different value of n 4, 5, and 6. And now the application 2 talk about smart grid network security and optimal control. The x of ut represent state variables, the network security level, and control variables u of t represent the network security investment. Problem statement, how to optimal a locally cybersecurity investment in the smart grid to maintain any acceptable level. System dynamic x dot of t represent the term of represent the natural degradation. Sorry. The cost function j and boundary condition, and what you find determine the optimal control u star of t and the optimal security trajectory x star of t, and satisfy the optimal dynamic and satisfy the boundary condition and minimize the total cost j. As a result, optimal locally of cybersecurity investment. Now move to the numerical result. The numerical result represent the x, the state error with the different value of n, 5, 6, and 7. Increasing n led to the smallest error that led to confirm the accuracy and efficiency of the proposed method. And the figure represents the result of the absolute error of the different value of n. And thank you. Anyone question? Anyone question?
Hello, Ms. Belsom. You hear me?
Yes, yes.
In the application one, please, can you show the slide?
Yes.
Application one.
Yes.
Well, what are the states and control variables? It's not clear here. Or the writing is so small, I can't see it, actually. I can't.
Please repeat the question.
What are the states and control variables of this problem?
The state represents the stored energy in battery, and the control represents the signal charging or discharging signal.
Okay, and application two, please. It's not clear.
Yes. Yes. What?
What are the states and control variables?
State variables represent the protection. Represent the security level, and control represent the network security investment.
Security level?
Yes, el state.
What do you mean by security level? How would you measure it?
About the result. The result.
Security level, you mean a security in an cryptography or what? What do you mean? شلون تقيسيها؟
وشو اقيسها بالنتائج اللي حصلتها.
لا مستوى I must speak English actually. How do you measure the security?
About the result, work.
Okay, thank you.
Thank you very much for your presentation. I would also like to ask one question relatedly. Are there other applicability opportunities for new math framework which works accurately for solar energy and network security? So what about the other real-world systems would you plan to test it on next as future research? Are you hear me?
Yes, but I can't understand.
I think that the sound is very low.
Yeah, yes. The sound is very low. So Your voice is a bit too quiet.
Please repeat the question.
Okay. Dear participants, thank you very much for your presentation. Now we can proceed our workshop with following presentation on the paper whose title is a hybrid image zero watermarking techniques based on signal neutrosophic domain and SVD, written by Hüseyin Kadim Abdali, Arej Abdurdayı, and Matej Abdul Numi. You may start your presentation, please, if you are ready.
Yes, I am ready.
Yes, please, go ahead.
Good evening, everyone. Good evening, everyone. My name is Hussein Kadam, and I am master's student at the University of Technology in Baghdad, Iraq. Today, I will present my research.
Can you share your presentation, please?
Yes, 1 minute.
Okay, thank you.
Is it okay?
Not yet. Yes, it's okay.
Okay. A hybrid image zero watermarking technique based on sigmoid neutrosophic domain and SVD. One minute. Motivation. There are three main points that motivate our work. Exacting zero watermarking methods often rely on unstable image features that degrade under common image processing attacks. This work addresses is a limitation by extraction more stable and robust image features. To exploit the structural representation of the neutrosophic T component with a block-based SVD for more discriminative feature extraction. To develop a reliable zero watermarking framework that preserves the original image while improving copyright protection and authentication accuracy. The goal of the work is develop and advanced zero watermarking system for digital image. They ensure robust protection of intellectual property right and preserve the original content without alteration. There are three mispoint problem statements. Step one, 1 point, common watermarking methods modify image content while many existing zero watermarking techniques suffer from unstable feature extraction under standard image processing attacks, reducing authentication accuracy. Moreover, intensity-based features often fail to capture robust structural information. Therefore, there is a need for zero watermarking framework that extracts stable and unusual feature without altering the original image. The proposed method addresses this challenge by combining the T component of the neutrosophic domain with a block-based SVD, generate robust features from secure watermark construction and reliable authentication without requiring the original image. Watermarking in digital image. A watermarking is a digital logo embedded in image to assert ownership and protect intellectual property rights. It can be used to prevent there is copyright modification or distribution of digital image. Watermarking technique is a digital technique used to embed identifying or distinctive information within digital content such as image, video, audios, or documents in a way that allows it to be later requires to prove ownership. protect copyright or verify the authentication of the content without acting is normal stability. Categories of watermarking. We have two categories. Number one is the zero watermarking, and number two is a traditional watermarking. Traditional watermarking definition. Traditional methods of adding watermark, logo, text, or symbol directly in the digital file, such as image, video, or documents, to protect ownership rights. The advantage is categorized by easy to application and extraction for ownership verification procedure. There is direct and visible protection of intellectual property when content is displayed. Zero watermarking definition, a method of protecting digital ownership without modifying the original file, keeping the content completely unchanged and preserving its quality. Advanced does not affect the original file quality, ideal for protecting digital content that requires maintaining the original quality. Types of watermark based on visibility and based on robustness and based on embedding domain. We in the research we work in the frequency domain watermark and based of type of data. Singular value decomposition (SVD) is a decomposition of any matrix A into three matrices A, U, sigma, V transpose. An orthogonal matrix representing the raw direction. Sigma, a diagonal matrix containing the singular value representing the importance of the each component in the matrix. V transpose is orthogonal matrix representation the column direction. The neurosophic theory, introduced by Florentino Simonelli, is a mathematical method for dealing with inaccurate or unclear information. Unlike classical logic, each element in the described by three independent parts: truth and indeterminacy and falsity. These three values is independent and do not have to add it up to fixed value. This makes the theory more flexible and helps represent an, uncreation and more accuracy because this is widely used in artificial intelligence and data analysis and image processing and discussion making system. The neurosophic domain in digital image processing, each pixel can be represented in the neurosophic domain using three membership value: truth, indeterminacy, and falsity. When image transform into the domain, a pixel PIG in the neurosophic image is represented as follows. This equation to be a neurosophic domain. Pixel the neurosophic domain. The three membership values defined by the following equation: truth membership function and indeterminacy membership function and falsity membership function. This original image used in my research and in the neurosophic domain, truth and indeterminacy and falsity. The diagram of zero watermarking construction, we input the original image and input the membership function to convert the original image to neurosophic domain and select T and apply SVD of each block from T, and we choose three cases to the matrix and the minimum diagonal and the maximum number of each sigma and convert the features to binary features, and we have make XOR between the binary watermark and binary features to get secret share. The diagram of the authentication procedure. We have XOR and we make XOR between the binary matrix and the secret share to get a watermark. Noisy attack and filter attack and image processing attack used in this research. We use three categories of attacks in this research. Noisy attack, like salt and pepper noisy, Gaussian noisy, Poisson noisy, speckle noisy. And filter attack, Gaussian low pass filter, motion filter, average filter, and median filter. Image processing attack, GPG comparison attack, and histogram attack. This a village route image used in the research after the attack. and we use the website of University of Technology, convert to a QR code watermark image and use it in the work. This table we show the NC and bear value with no attack for 3 cases. This the result of the NC and bear and the noisy attack. We can see the result is robust, and this result of filter attack for NC and bear value and this image processing attack result NC and bear values is and robust. Recovered watermark image for the 3 case for a villager award image. This recovered watermark image after extraction, after attack. Sorry. Conclusion: the proposed method introduce a novel neurosophic truth membership function that extract stable structural features for robust image authentication by combining the neurosophic domain with SVD. The framework achieves blunt zero watermarking with high robustness against various attacks while preserving the original image. Experimental results confirm the effects and demonstrate the potential of the neurosophic representation for future adaptive watermarking system. Thank you. If anyone have question.
Thank you for your presentation. The presented paper developed a novel polynomial-based framework for solving continuous optimal control problems accurately and efficiently. The authors are motivated by challenge of this as a result of high computational costs and the limitations of existing approximation techniques. A new class of basis functions, namely the extended complete White-Capel polynomials, is introduced. Numerical results indicate rapid convergence and high precision, with the obtained solutions closely matched exact and benchmark solutions. These findings establish the proposed method as a reliable and powerful tool for a broad class of optimal control problems. Would anyone like to pose a question about these papers? Please, you have?
Okay. How are you? Just want to ask you about the method you are using with the watermark. Okay. Are you hearing me?
Yes, I am here.
Okay. You said you were using SVD,
Yes.
and you used zero watermark, which means you are extracting information and make it as a watermark, and this watermark will not be changed because it is not actually you added information, it's actually you are extracting information. The attack you did, what type of attack you just attacked the picture of the watermarked image? What type of attack?
3 type of attack: noisy attack, and filter attack, and image processing attack.
What do you mean by filter attack?
Yes, this is my filter attack.
What do you mean by it? What type of filtering you applied?
A Gaussian low pass filter, motion filter, average filter, a median filter.
Okay, great. So which one of them is making the worst effect on the watermarked image?
This is the effect in the result. The motion filter is a big effect at the watermark image.
So the worst effect is the motion filter.
Yes.
What do you think you could do in the future to improve it, or to get rid?
In the future, I can improve the SVD and make with SVD improve SVD and with a microscopic domain and machine learning in the SVD.
What would you do with the machine learning?
To select the feature.
You mean to select the watermark?
No, select the feature, and because I am extracting the feature from image, I am using the machine learning and the program training to select the best features in the image.
Features. Okay.
Okay.
I did as a picture. Sorry. Okay. Thank you very much.
Thank you.
Thank you very much for your presentation and for your answer. Dear participants, we can now proceed our workshop with the following presentation on the paper who is titled as a hybrid image zero watermarking technique based on sigmoid. Close mode. Thank you very much for your presentation. Now, dear participants, we can now proceed our workshop with the following presentation on the paper who is titled Applied Linguistic Dynamic Models and Lexical Choice in Mental Health, new by Audrey Dursun.
Thank you. Can you hear me?
Yes, please.
Okay, so you can see my slides as well, I suppose. Good afternoon, esteemed participants. This is Audrey Dursun from Istanbul Ticaret University, Istanbul, Turkey, and my presentation is about the paper entitled Applied Linguistic Dynamic Models and Lexical Choices in Mental Health News. Before moving on to the details, I would kindly share you the outline of my presentation today, as you may kindly see. Following this outline, we may briefly address the background and problem identification of this current study. Let me say that language and lexical choices or word choices in media, particularly in health news, are critical because they have effect on shaping public perception, understanding, and responses to medical information and content. The language and words used in news are significant because they also make a subtle difference in the way readers or viewers perceive the story. This point emphasizes the need to choose the words carefully so that content can be understood clearly without bias or without misleading content. Accordingly, lexical choice refers to word or vocabulary that is varied with particular form or style of the text, personal judgment, cultural or background of the writers. So, lexical choice in media signifies a kind of deliberate selection of specific words, phrases, and terminology from the side of editors, journalists, and reporters, and this shapes meaning, tone, as well as audience perception, as I have mentioned. And this process is actually a strategic one. And according to critical discourse analysis, this is a non-neutral one because it may reflect organizational bias or preferred ideological framing of events. So this is also what is conveyed by linguist Van Dijk, who states that words are never neutral, and the choice of one word over another reveals the writer's ideological bias, political perspective, or underlying attitude toward the subject. And when we look at public health matters in news media, this is really important while framing public opinions, raising public awareness, and acknowledgement of public health issues and affecting the making of policies. On the positive side, it might reduce stigma if this reporting is sensitive and responsible. It raises awareness regarding mental health problems by providing accurate and empathetic information to promote help-seeking behaviors and personal stories. On the other hand is that the impacts could be seen negatively, adversely, like sensationalizing, exaggerating, and or trivializing issues related to mental health and spreading misinformation, which is actually the core of this study. These might also cause stereotypes to be reinforced And negative emotions like fear, sadness, or anger could be triggered as a result of wrong or irresponsible reporting. It has been reported by research that media contribute to mental illness stigma through their exaggerated, comical, or inaccurate images used for portraying individuals with psychiatric disorders, as well as providing incorrect information about mental illness. Another point to mention is the concern that representations in the press are disproportionately negative. And one analysis we can give example carried out based on the UK daily newspapers demonstrated that half of the articles on mental health were negative in tone, and their analysis revealed some kind of over-lexicalization and also relationship and association of mental illness with violent contexts. In addition, this is important, linguistic evidence should be taken into account before one prepares the guidelines about the linguistic forms for discussing mental illness in the press. And another significant change as a suggestion to overcome these problems for journalists is to accurately depict the symptoms of mental illness and ensure that the symptoms of mental problems are contextualized appropriately. So this accurate and responsible reporting, reporting. Okay, when we come to motivation and aims of the study, we have seen that, and as the amount of research and literature has revealed, mental health news, media, and use of language make up a significant line of research. And the number of studies regarding news media portrayal of people with mental disorders for the country Turkey context is relatively limited when it is compared with studies carried out in different countries, especially in the West. So motivated by this gap and also the critical role of language and this negative news coverage in mental health topics, the current study aims to provide inputs through its analysis of news articles within an applied linguistic dynamical model framework used for evaluating inaccurate content, misleading information, and or stigmatizing descriptions based on the lexical choices present in the news texts regarding mental health, people with mental health problems. And as you can see in the materials and methods section, especially about the materials part, the data set of the study includes a total number of 725 newspaper articles about mental problems and people living with those problems. The analyzed newspaper articles had been retrieved from the electronic sites of 6 daily national newspapers published in Turkey in Turkish language. And Table 1 presents the breakdown of the news articles by the newspaper. The selected newspapers for the dataset are popular and highly circulating ones in the country. When we look at the methods briefly, the study has made use of both qualitative and quantitative content analysis to analyze the lexical choices, which are specified, as you can see in the slide, as inaccurate wording, discrediting, stigmatizing language phrases. These lexical choices are linguistic features used in the newspaper texts regarding mental health, mental problems, and people having mental conditions. And there are 2 dimensions to achieve these analyses for the evaluation. One is the theoretical one, including the content analysis of the linguistic features, and the other one is the quantitative elements, which is the time frequency statistical analysis, which is a category of descriptive statistics. If we look at the definition of applied linguistics in a brief way, we know that it is an interdisciplinary field, and its aim is to identify, examine, and provide solutions to real-life problems related to language. From communication research to psychology, as well as education, sociology, and anthropology, it is related to different academic areas, and practical use of language is addressed by applied linguistics. And in journalism scope, applied linguistics analyzes the use of language, discourse, and media practices so that communication quality can be improved and societal impact can be comprehended. So this combination between applied linguistics and media also helps researchers explore intersecting aspects of language, communication, and technology. From the applied linguistic points of view, this present study employs content lexical analysis so that it was possible to address the use of language in the news articles based on the problem that there is a disproportionate amount of negative news content of mental health and people with mental health problems in news media. As we said, the second dimension of research is related to quantitative part, and time frequency analysis has been resorted to in the study. Time frequency is used for understanding the distribution of data in the time frequency domain to be able to detect and separate the components of signals with non-overlapping components. It is also important to observe the prevalence of certain categories and identify possible imbalances within the data set. And actually, when a frequency table is constructed, we can have the observation number in each class as the explanations on these slides and the formula on this current slide shows related to time frequency analysis and steps of preparing the frequency table. So after materials and methods, when we move on to experimental results and discussion, based on the content analysis and frequency results, it has been found that the highest inaccurate or misleading content was in Sabah newspaper, and this was followed by other newspapers, as you can see the number of items with inaccurate or misleading content. And figure 4 depicts the results based on computational linguistic analysis by the newspapers. In the following 3 slides, I would like to show you the representative excerpts selected as 9 news items from the dataset to provide evidence regarding sensationalizing, inaccurate, and stigmatizing reporting. And these are some exemplary cases from the large data set. Our aim has been to identify and evaluate inaccurate content, misdescriptions, and category mistakes. To give one example, for example, when we look at the interpretation of these examples related with theoretical aspects, we can see that there is a kind of category mistake in bipolar disorder. Because bipolar disorder is categorized as a mood or affective disorder, but in 2 of the news items, as shown here in red color, it has been identified inaccurately and described as bipolar personality disorder or manic depressive personality disorder. Actually, it is not. It is an affective disorder. So such taxonomic category errors in terminology could lead to real-world misinformation as a negative outcome. Here, theoretically, we may also mention framing in communication theory as put forth by Entman. It describes the process where particular aspects of an issue are emphasized and while others are excluded. We also see stigma, which comes to the foreground as another related theoretical aspect developed by Goffman. Goffman defines stigma as a profoundly discrediting attitude, reducing a person from a whole and usual individual to a discounted one. For example, one news story about violence against women actually is about this one. A businesswoman, actually, who is a non-expert, gives her opinion about bipolar disorder using derogatory language. For example, saying that there is a disorder named bipolar. 700,000 bipolar patients wander in the streets. First of all, there is no statistical evidence here, which is not very accurate. Plus, these are at banks, the non-expert says. So grammatically, the use of demonstrative pronoun these is labeling actually, and it is an example of discrediting language, which refers to the use of words or phrases designed to weaken a person's or a group's reputation. So there is the lack of statistical reference And also there is the inclusion of a non-expert's opinion in the news items. And this slide actually shows the general points which were detected in the data set about examples of misleading and inaccurate reporting. Victimization frames were also encountered, especially about the people who attempted or who committed suicide. They were named as suicide victims, but this suggests medical passivity due to the fact that the person is portrayed as a passive victim or sufferer rather than an agent in their own recovery. It has a negative result because the focus is on tragedy and hopelessness rather than on recovery and management. Another news item asked the question, are comedians mentally ill? This kind of news actually points something related to weirdness, which is also a stigmatizing frame because strangeness of the behavior is highlighted. Actually, anyone in his or her lifetime could encounter this kind of a disorder, a mental disorder, which is normal, just like physical illnesses. So after these interpretation of the news items, actually, we have seen that there are language and lexical choices in mental health news, which could be stigmatizing, discrediting, or labeling, making the frames of dangerousness, victim, and weirdness more salient, more evident than others. Okay, this recapping note leads me to the conclusion and future direction parts of the study. Word choice needs to be considered carefully, as I have said at the beginning, and it has been often reported that media contributes to mental illness stigma through exaggerated, comical, and inaccurate images, portraying individuals with psychiatric disorders, as well as providing incorrect information about mental illness. And the findings of the current study are in line with these considerations, since the representative sample revealed that linguistic and lexical choices in mental health news can be stigmatizing, with dangerousness, victimhood, passivity, and weirdness frames being salient. So, as some future directions based on these results, we can say that the language model and linguistic structure proposed in the study can be used for making standardization guidelines of language use within responsible, sensitive frameworks. Also, it can be suggested that linguistic evidence should be taken into account before preparing the guidelines on materials on health and other critical topics that concern human life. So these notes bring me to the end of my presentation. These are my references. Thank you very much for your kind attention.
Would anyone like to pose a question, please, about this work and presentation? Okay, I would like to forward a question about your work. What are some limitations related to the language model and the structure proposed in the study? Yeah. Sound.
Media means covering a broader range of news media from social media platforms and other materials. Also, maybe differences between cultures and countries could also be pointed.
I think you need to close it. Your internet connection is we cannot hear you.
I may say again. I have tried to answer the question, but let me say it again. I said the period of analysis is 5 years, which is limited actually. This could be considered as one limitation, and it can be further extended to cover more years. And there could be some comparative analysis made between different cultures because these newspapers were only from one country. So in terms of data set scope and size of the data set, the scope can be extended, and other platforms can also be considered, other print media, including social media platforms. So only print media could be considered as one limitation of the study, as you have asked.
Do you have any question? Could I ask you a question? How did you make the analysis? Actually, I did not get it. I'm sorry.
How did I make this? Sorry, could you repeat the question?
The analysis.
The analysis, yes, it was on two dimensions. One was a content analysis of the lexical choices. It was content analysis from social sciences. The other one was quantitative. We carried out time frequency analysis, which makes up the quantitative part of the study. So we used
the content analysis, how did you perform it?
Through SPSS.
SPSS?
Yes, SPSS program, statistical software program for the quantitative part.
Oh, so you just analyze the data you are getting from the data set?
Yes, I selected the data from the news items through some keyword search from the electronic website of the newspapers, and the inputs were put on statistical package, SPSS, and the inputs were analyzed accordingly.
So you made the data acquisition, then you fed it to the SPSS, right?
Yes, it was created just like you mentioned, yes.
Okay, thank you very much.
Thank you too, thank you.
Thank you for your presentation and answers. As we are proceeding, the next presentation in our workshop will be for the paper entitled Internet Market Analysis Influence of Brand Technical Indicators using Erimax Modeling for Improving WTI Crude Oil Price Forecasting. If you are ready, you may go ahead for presenting your work, please. Yes, please.
Sorry, I want to share the presentation first. Okay. So, hi everyone again. Now we talk about another subject, which is intermarket analysis, influence of brand technical indicator using Erimax modeling for improving WTI crude oil price forecasting. First, we need to know what is forecasting. Forecasting is a technique that uses historical data as an input to make informed estimates that are predictive in determining the direction of future trends. So we have a historical data and we can predict the future trends. It's used in agriculture, healthcare, sales, cloud computing, and crude oil industry. And our work is about crude oil industry. What do you mean by crude oil? Is the mixture of petroleum, liquid, and gases extracted from the ground by oil wells. It's an essential source of a fuel, of course, and it is used to produce several products. What is the motivation that makes us think in this subject? Today, the crude oil is one of the world's primary energy sources and have a tremendous influence on the world. And because the rapid change in the price of crude oil, for example, the rise or fall affect economy activity directly, as we will see. So the oil price forecasting is very important and has gotten much interest from both researchers. Most studies on forecasting crude oil occurred by using a traditional machine learning. And what's the problem with the traditional machine learning is that we have something called, we have two terms, stationary and non-stationary. Okay, and these two terms are very important. What I mean by stationary, it means that the mean and variance are fixed over the time. So even when we draw it, it's give me a line, okay? And non-stationary Okay, it means that the mean and variance are increased and decreased over time because the impact of many factors. And this is what happened really. So the machine learning just solved the problem of the stationary, and it's not suitable for what happened in the world, for example, the Iraqi-Iran war or COVID-19 or any other external environment. So if we see this figure, we see that here, I don't know if it's clear or not, Iran-Iraqi war, 11 September, and a lot of, and we see the price of the oil decrease and increased, depends on the situation or on the external environment. So the stationary, we can't depend on it at all. It's a variable, it's a multi-dimension that we need to guess. Okay, so why we think in this to solve this problem? Recently, in numerous empirical studies used ANN to solve the problem of stationary to be non-stationary. Okay, they used recurrent neural network and a lot of things that multi-layer perceptron or anything related to deep learning. Deep learning has different challenges. It's, as you know, we need to have a large data set to train the models. Okay, it's expensive. We need a high CPU rate, space, memory space, disk input, output, and so on. So deep learning is not an easy task. Why? Because we need to tune the hyperparameter, determine the number of layers in this, in the model that we choose it. The deep learning required amount of data, large data sets, maybe because of a lot of training, we reach an overfitting, vanishing gradient problem, and a lot of problem. So here in this proposed really a new methodology. We proposed something called, we use two different type of oils, and we get a feature from one type from a print and uses as a variable in the other type to predict its price. Okay, so first, this is the diagram. We combine these two to make them, both of them, like the same time series. Okay, and we generate the indicator technical, and that after this we use some. We will see it later, and I discussed one by one. The data set we used here, it's WTI, it means West Texas intermediate crude oil. And we have a Brent oil. So we have two data sets, two different data sets. The thing that we need to focus on it, in forecasting or in time series, we have just two columns always. It's the date, okay, and the price for oil, I mean, or any other things, not just oil. We have date and time. Now, in this proposed paper, we do a different things that we can increase the features that one type of oil have it, not just the date and the print. Okay, so we first merge them. We are, sorry, I can't see, casting the data, and then we following. You know always that, for example, in Thursday, okay, the oil, the prices is stop to change. So what we use to follow it, we use, for example, for Friday and Saturday, we use the Thursday prices to follow the missing data. So as you see, we have here in the red color, we follow the same price of the Friday and of Thursday to follow the data. Okay. The idea here is to use a statistical methods, not deep learning, a statistical methods. And we have something called ARIMA, okay? And you will see what do you mean by it, okay? And we have something very new. It's called ARIMA X. They added a variable named X to this ARIMA. And from this variable, we can extract a technical indicators as a feature, okay, and add it to the first table that we see is just the date and the price. So before generate any technical indicator, we should talk about its technical indicator as a mathematical tools used to determine whether a stock is oversold, overbought, or price trend is weak or strong, and therefore to forecast its future price movement. There are a lot of or many technical indicators. We use the more standard one, which is a simple moving average, exponential moving average convergence, and velocity or standard deviation. And this is the equation of each one. Then, by using this above equation, we will generate a technical indicator. From where? From a brand. To use it where? To predict the WTI oil price. Okay, so as you see before, we have just two, date and time. Now we have a different features. If you see, this is the feature extracted from this technical indicator, depends on the equation above. Okay, so we get like a different features. If you enlarge it, you can see it on different lag. There's a lag, okay, and they give you the print. We extract all these features from a print. So if you read it, it's a print, and this time print, and so on. So we extract an additional features, okay, using a technical indicator. As you see in this table also. And what we use later, we use something called ARIMA X. But before we talk about ARIMA X, we need to see the hierarchical of this ARIMA. They start with autoregressive AR only, then they added moving average MA, and then autoregressive moving average, then autoregressive integrated moving average, until they reach to ARIMA X, which is autoregressive integrated moving average with exogenous variable. And this is what we need, the X variable. The equation for this ARIMA X model is here, and we need to know these parameter. The P parameter indicate the number of flag previous period of the previous day, and D, measurement the number of differential transformation performed to eliminate the trend or seasonality, and Q parameter indicate the number of flag of a previous error. So this is the difference between stationary and non-stationary, if you see it. The stationary, it's in the green, and non-stationary is in the red color. We measure the system by using the root mean square error, the mean absolute error, and the mean absolute percentage error, and R squared. Okay. What we need to know, if I used ARIMA without technical indicators that I talk about it, which is the, say, the proposed idea. If you see this, figure, the green one here at the end is a linear line. So this is this linear line with the orange one, it means the expected in the future and the old one. And we see there is no relation between them. This is just a stationary line, and the other is a multidimensional line or a movement. So when we add a technical indicator, we just see, we start with the one, ARIMA without any technical indicator, and we add one by one, which is called appellation, one by one technical indicator, until we reach at the end, really, it's like both of them, they are just matches. One above the other. Okay, so this, we can reach this value by using the technical indicator. We talk about it. So we see our result, okay, in G, we are enhancing the mean square error, root mean square error, and all of them. If you see it, there's a different, this is 2.9, the previous one is 4.1, this is a 3.9, the previous one is 5. So we get really perfect results when we use technical indicator. And the most important thing, that we can deal with non-stationary data. Okay? So finally, the conclusion is, adding an exogenous variable to an ARIMA forecasting model can allow ARIMA to capture a price, the change in a price, say like this, okay? A technical indicator generated from another time series was inputted, was inputted the machine learning, يعني it's better than machine learning or deep learning. And despite the variance between the WTI and the Brain databases, the above experiment result reveals, the relationship between the two data sets without use it. And thank you very much for listening. And any question?
Dear Suad, thank you very much for your presentation.
Thank you for
Thank you. And
of course, Dr. Vinod, have a question?
yes. Are there any question about this presentation? Please, go ahead.
Hi, Suad. It's interesting what you did, but actually, I just want to ask you about one thing. You said you might take a feature from the Brent, for example, oil, and feed it to the expected, to improve the expectation to other type of oils, right?
Yeah.
Okay. Are they of the same time, or is it historical? I mean,
yeah. What do you mean?
I mean, if you have a data set for example, 3-4 years ago, right?
Yeah.
You are getting this, the expectation for this year or the next year, for example, from utilizing the historical case and the feature from, for example, the Brent, is it from a historical case or is it from the current case?
It's, I don't understand exactly, but it is not a real time. It means Brent oil, it's a historical data found in American, it's a standard data set found in American, but it's have a period from, say, from 2023 till, for example, 2025, something like this, but it's a historical, okay, data set. It's not a real time or live streaming that we get the data directly.
I understand now, because I thought you were talking about getting the current value of the, for example, the Brent, and you are feeding it with the historical data so that you can get the new or the current value of the other oil.
Really, it's a nice idea. You can do it using Kafka or something in big data, live streaming. Yeah, it's a nice idea. You'll do it.
I think you did ignore one of the most important factors. It's the political factor.
The political factor is found. I said the war, I said the 11th September, I said everything. And if you see the figure that I talk about, it, the price of the oil decrease and increase based on these factors.
Okay,
so
did you
get this
training?
What?
Did you get the factor? I'm just asking because it's interesting. Did you put this factor inside the training as part of the data?
Of course, Doctora. We put it inside the training. We divided the data to train it. So we put it inside the training, depend on this technical indicator. And we have a lot of really or more technical indicator. We take just the foremost. Maybe another technical indicator give us a better result, but the result we reach it's very good, really. And this subject really is very, very interested. And when we work with it, it's like a novel when we work with it. and we need to enhance it, maybe to make it a live stream or something like this.
Thank you very much.
Thank you,
you
Fuat.
for your
May I ask a question, please? What may be some possible future directions what may be some possible future directions with relation to your work about the detectors handles?
I don't understand the question.
Future work for you.
Yeah.
About detector handling.
Sorry, what? Give what?
Future directions.
Future directions, yeah?
Yes.
Yeah.
Directions.
Future or feature?
Future or future directions, okay. For this work, the future direction, we can increase the number.
About the detectors handled.
Yeah. If you mean what is the future direction for this subjects, we have more than one future direction. One of them is to increase the number of technical indicators that may affect or take another type, not just Brent and crude oil. Maybe we take Oman oil, maybe we take any type of oil. This is first. And really the thing that Dr. Vinos talked about it, maybe we make it as a live streaming directly. They take these features and they analyze it directly or as real time, not real time, say live streaming.
Okay. Has there been any limitation of this scheme?
Till now? Really,
Yes.
It's no limitation, but of course we can enhance the results. It's not limitation. When we work it, there is no limitation because ARIMA X is perfect, really. The X variable make a flexibility to deal or to convert the type of analysis from stationary, which is the mean and variance is constant, to non-stationary, a multidimensional. So there's no limitation, but of course we can enhance it in the future.
Okay. Thank you very much for your presentation and answers, Tuğba.
Thank you.
And dear participants and our colleagues, this brings us to the end of our workshop. While concluding our workshop, I would like to thank all participants for their valuable contributions through their papers and presentations they have delivered. We hope to meet you all once again in our further academic events. I think we can go on, enjoy the remaining part ICCSA 2026 conference in this beautiful country of Portugal and love city Braga. See you. Hopefully, meet again.
Hello? Hello? Hello, we still have another one.
Yes. I think the chair just left, so wait, I will try to fix it. Just one second,
I see.
please.
Okay. All right. Is that they think they already finished? Because I'm the last presenter.
Yeah. Just give me 1 minute.
Okay,
just in case I will finish sharing the session.
I see. Thank you.
Okay. I think we can keep on with your last presentation. So please let me introduce you. So the next paper is Quantitative and Qualitative Comparison Assessment of Edge Detection Algorithms for Robust Image Processing. And the speaker is Noura Malina Yamaluddin, right?
Yes.
Okay. So Please proceed further. The floor is yours.
Okay, thank you. Let me share my slide first. Can you see my slide?
Yes, maybe try to put them full screen.
All right. Now can you see?
Perfect.
All right. Okay. Okay, I will start. Assalamualaikum warahmatullahi wabarakatuh and good evening to everyone. I am Nur Amalina binti Jamaluddin from the Center for Foundation Studies at the National Defence University of Malaysia. Today, I will be presenting our research paper entitled Quantitative and Qualitative Comparison Assessment of Age Detection Algorithms for Robust Image Processing. This study provides an in-depth comparative evaluation of fundamental age detection techniques, specifically the Laplacian and Kenny operators, exploring the critical trade-offs between mathematical precision, noise robustness, and computational efficiency. Why I can... Okay, all right. In this slide, here are our main concept with the abstract age detection fundamentals, Laplacian age detector or LED, Kenny age detector or CED, application areas and use case, comparative analysis between the LED and also CED, conclusions. I cannot press the next slide. Why? Sorry?
Try pressing the space bar on the keyboard. Normally it works.
Oh, okay. The space bar. All right. Okay, thank you.
You're welcome.
Okay, to begin with, this study offers a mathematical comparison between the Laplacian age detector LED and the Kenny age detector CED. Age detection is a foundational tool in computer vision, serving as a critical first step for complex tasks like object recognition, image segmentation, and image enhancement. Ages are vital because they encode structural boundaries and present local discontinuities in image intensity. With the explosive growth of artificial intelligence in fields like autonomous navigation and health informatics, selecting the right age detector is paramount. While many cutting-edge deep learning or quantum approach are emerging, classical operators remain highly valued due to their explicit mathematical foundations. However, practitioners often struggle to balance the trade-off between simple, fast algorithms and complex, heavy pipelines. Our work bridged this gap by providing a definitive benchmark. And then what is an age in an image? Age detection identify regions of significant intensity change, essentially object boundaries. There are two main mathematical approaches, gradient-based methods like Sobel and Pruitt, which use first derivative and second derivative methods like Laplacian and LOG, Laplacian of Gaussian, which examine the rate of intensity change. And then for the Laplacian age detector calculates the second derivative of intensity, a more refined version. The Laplacian of Gaussian or LOG incorporates smoothing to reduce noise. While LED is simple and fast, its drawbacks include thicker edges and higher noise sensitivity. Okay, for the Kenny age detector, they use a 5-step noise reduction with Gaussian filtering, gradient calculation, non-maximum suppression to thin edges, double thresholding, and age tracking by hysteresis. CED provides high accuracy and excellent noise resistance but at a higher computational cost. So now let's look at the real-world use cases. LED is best suited for applications requiring speed and low computational resources. These include real-time system, basic object detection, barcode scanning, and industrial automation. High-speed image processing in embedded system, basic object detection such as barcode scanning, real-time system with limited computational resources. Meanwhile, for the Kenny age detector is designed for application requiring high accuracy and noise robustness. CED shines in applications needing precision, such as medical imaging, robotics, surveillance, and autonomous vehicles. Its ability to handle noise and define clear object boundaries make it ideal for complex image segmentation tasks. So here we have the comparative analysis between these two age detector, LED and also CED. In summary, We can see that LED is faster and more efficient, but it suffers from noise issues and produces thicker edges. CED, although slower, excels in delivering cleaner and more precise edge detection results, especially in noisy environments. So this research paper provide a comparative evaluation of prominent edge detection techniques, specifically contrasting the Laplacian edge detector with the Kenny edge detector. By assessing mathematical foundations and experimental metrics, the authors demonstrate how incorporating Gaussian smoothing creates the Laplacian of Gaussian LOG model, which significantly reduce noise sensitivity. While the basic LED is noted for its computational speed, it's often produced inaccurate edges compared to the more sophisticated multi-stage Kenny pipeline. So this study established that CED remains the most robust choice for precision-heavy tasks like medical imaging, despite its higher processing demands. Here we have in the table 1, we have a quantitative result to support the analysis. Okay. We have the quantitative performance matrix for LED variants, which is provide a numerical breakdown of how 3 different Laplacian-based edge detection methods perform across 6 specific metrics, comparing them against target optimal range. So we can see from this, the basic Laplacian edge, the LED, is the faster method with a processing time of just 45.2 millisecond, but it fails to meet the almost all optimal quality targets. And at the same time, in the signal and structure, it falls short of the greater 20 decibel target for peak signal to noise ratio, PSNR, at 18.42 decibel and miss the greater 0.8 target for the SSIM. The SSIM is the structural similarity index at 0.651. And the accuracy and noise, this edge accuracy, FN score of 0.634 is below the greater than 0.7 its noise sensitivity. 0.23 is worse than the less than 0.2 ideal limit. And for the edge thickness, it produces the thickest, least precise edges at 3.2 pixel, while the target is less than 2.5. Okay, we look at the LED plus Gaussian smoothing. From here, it creates a balanced middle option that notably improve quality but increase the computational runtime. The improvement in this LED plus Gaussian is successfully is the optimal targets for PSNR 22.85, decibel, edge accuracy 0.721, and noise sensitivity. Despite this improvement, it still fails to reach the optimal SSIM target 0.742 and produce edge that are slightly too thick, 2.8 pixels, compared to the less than 2.5 target. Its processing time also rise to 67.8 millisecond. We can see from the LOG, this method is the slowest but highest quality option, successfully meeting or exceeding every single optimal range evaluated in the table. Okay, about the peak quality, it achieved the highest PSNR 25.73 decibel, the best structural SSIM also, and the highest edge accuracy F1 score. It has the lowest noise sensitivity 0.14 and is the only LED variant to successfully meet the target in precise edges at 2.1 pixels. So in this table 1, it demonstrates the trade-off between the computational speed and detection accuracy. As you progress from the basic LED to LOG, processing time essentially double, but the overall quality, structural fidelity, and noise robustness improve significantly, enough to meet all optimal performance threshold. So next we go to the figure 1. It provides a visual quantitative comparison between the raw Laplacian edge detected LED and the improved Laplacian of Gaussian LOG method. It used a bar chart to contrast their performance across 3 key evaluation metrics, the PSNR, the SSIM, and also noise sensitivity. So from this chart, it illustrates that aiding Gaussian smoothing enhanced the overall signal quality of the image. The LOG method achieved a higher PSNR of 26.75 decibel compared to the raw LED's 22.18 decibel. With the SSIM, okay, this metric evaluates how well the structural integrity of the original image is preserved during age detection. LOG significantly outperforms the raw LED with an SSIM score of 0.74, whereas the raw LED scores much lower at 0.54. From the bar chart, noise sensitivity, the raw LED demonstrate a high vulnerability to noise with a measured sensitivity 41.2%. So in contrast, the LOG method nearly half this vulnerability, reducing the noise sensitivity to 23.5%. So this clearly highlights the LOG method enhanced tolerance and superior robustness when processing noisy image. Next, in this figure 2, it provides a comprehensive 4-panel visual breakdown of the quantitative performance and trade-off among the 3 Laplacian edge detector LED, basic LED, LED plus Gaussian smoothing, and LOG, Laplacian of Gaussian. It visually graphs the metric data discussed in table 1 to illustrate how this method compares against optimal performance threshold. So from the PSNR comparison, this bar chart illustrates the signal quality of each method. So it visually demonstrates that LED 18.42 falls below the acceptable quality threshold of 20 decibel, while both the LED plus Gaussian 22.85 decibel and the LOG variant 25.73 decibel successfully exceed the target. And then for the SSIM comparison, so this chart compares how well each method preserves the structural integrity of the original image. The visualization shows that only the LOG method 0.823 surpassed the good threshold of 0.8, whereas the basic LED 0.651 and the LED plus Gaussian 0.742 failed to meet this standard. And then for the noise sensitivity comparison, in this metric, lower values indicate better performance. The chart highlight that the basic LED is highly vulnerable to noise 0.23, sitting above the acceptable limit of 0.2. Adding Gaussian smoothing brings the sensitivity down to an acceptable 0.18, and LOG achieved the base noise suppression with a low score of 0.14. And then in the last graph, we can see the processing time versus edge detection accuracy. From this scatter plot provides a direct trade-off analysis by graphing processing time against edge detection accuracy, F1 score. It visually plot the basic LED at the bottom left, indicating it is the fastest but least accurate. LED plus Gaussian in the middle, and the LOG at the top right. So this effectively illustrates that achieving the highest edge accuracy with the LOG method requires sacrificing computational efficiency, as it is the slowest method at 89.4 millisecond. So overall, from this figure, visually reinforce the study's conclusion that while LOG provides the strongest quantitative performance among the Laplacian method and meets all the threshold, it fundamentally requires a trade-off with increased processing time. Okay, next, from this figure 3, this image shows a 2-line graph comparing the performance of 3 different LED variants under varying levels of image noise. Okay, from the sigma equal to 0 to sigma equal to 40. So we can see here the basic LED on the pink line and also the LED plus Gaussian in a yellow line, and LOG on the green line. Okay, so we see on the left graph here the edge detection accuracy versus the noise level. Okay, so this graph uses the F1 score on the y-axis to measure how accurately the algorithm detects edges. And F1 score closer to 1.0 means highly accurate edge detection. Okay, the threshold, there is a red dash horizontal line at 0.7, which represent an acceptable threshold for accuracy. Okay, and then on the right graph, this graph use PSNR, measured in decibel on the y-axis. Higher PSNR indicates better, cleaner signal or image with less distortion. So the threshold, a red dash horizontal line is set at 20 decibel, representing the minimum acceptable signal quality. So LOG maintains superior image quality, staying above the 20 decibel threshold across almost the entire noise spectrum, only touching it at extreme noise, the sigma equal to 40. Meanwhile, for the LED plus version, the yellow line, okay, starts strong but falls below the acceptable 20 decibel quality after the noise level passes the sigma equal 20. And then for the pink line, the basic LED stays completely below the acceptable threshold at all times, proving highly sensitive to noise. So I can say here the basic LED is notoriously sensitive to noise because taking derivative, which is how edge detection works, amplify random background noise by smoothing the image first using a Gaussian filter or ideally using the LOG method. So the noise is suppressed before the edges are detected, leading to the significantly better performance shown in the green line. Okay, next in the figure 4, okay, this image presents a quantitative performance and noise sensitivity analysis comparing 3 distinct implementation of LED under varying level of image noise. The sigma equal to 0 to 4. Is that same? Okay, wait. I think this one same, sorry. Okay. In figure 5, okay, this image displays a 4-part computational and parameter analysis of the 3 Laplacian edge detection LED, basic LED, and also LOG. While the previous figure showed that LOG has the highest accuracy, this figure highlights the trade-off in time, memory, and parameters tuning required to get that premium performance. Okay, LOG is the robust champion if precision, accuracy, and noise immunity are critical, medical imaging, or autonomous driving. LOG is the optimal choice. It maintains an acceptable accuracy threshold with the F1 score is 0.7 and signal quality, the PSNR, for 20 decibel under 20 decibel under heavy noise level where other methods fail completely. For the basic LED is fast but fragile. If memory and processor are severely limited, low power, microcontrollers and the input image are perfectly clean. Basic LED is viable due to its high efficiency. However, it is entirely unsuited for noisy environment. Okay. The conclusions for this study established a clear trade-off between computational efficiency and detection accuracy among the evaluated edge detection algorithm. From the image, the CED emerged as the most robust and precise method overall. Its multi-stage pipeline produced the cleanest, and most continuous edge maps, making it the preferred choice for applications requiring high accuracy, such as medical imaging and autonomous system. However, it demands the highest computational load and is highly sensitive to manual parameter selection. And for the LOG, Laplacian delivers the best quantitative performance among Laplacian-based method, offering a strong balance between noise suppression and accuracy. It significantly outperforms the basic LED across all quality metrics, though it requires heavier convolutional operation that increase processing time. So, okay. And then the choice between these two algorithms depends on the specific requirements of an application. LED for speed and simplicity, CED for precision and reliability. So, for elements such as adaptive thresholding and multi-scale analysis can further enhance their effectiveness in real-world scenario. Okay, thank you very much for your kind attention. Any question?
Thank you very much for your presentation. Do you have any questions? Okay.
So, sorry, example.
Yes,
please. Miss Karaja, the LED is the fast computational efficient method suitable for basic object detection and real-time applications. Did you do the real-time application?
Sorry, we don't do the real-time applications. We just refer the set standard for reference image.
So you didn't do the real-time application?
Yes, yes, no.
Okay, thank you.
Thank you for your presentation. Now that all participants have completed their presentation, we can close this session. The final part of our workshop will take place July 2 at 4 p.m. We look forward to seeing you all there. Thank you for your participation. Thank you.
Thank you. Bye.
Bye.
Bye.